Hey everybody, in this video, we are going to do one free response question based on the topic of kinetics, which is this unit. So this is from the AP chemistry exam, and let's read on. So, nitrogen dioxide, NO2, is produced as a byproduct of the combustion of fossil fuels in internal combustion engines. At elevated temperatures, NO2 decomposes according to the reaction below. 2NO2 becomes 2NO plus O2. The concentration of a sample of NO2 is monitored as it decomposes and is recorded on the graph directly below. The two graphs that follow are derived from the original data. So I would immediately try to find the line. This one is a curve, this one is a line, and this one is a curve. So let's see what A says. Explain how the graph indicates that the reaction is second order. Well, the reaction is second order because the graph for 1 over the concentration of nitrogen dioxide versus time is linear, and that's all you have to say. Write the rate law for the decomposition of NO2. Well, we see in our reaction that NO2 is our only reactant, so I am assuming that we don't have to worry about anything else for now. So rate is equal to K times the concentration of NO2 squared. And I'm not worrying about anything else for now because they don't introduce any other chemical that we should be worried about. So for now, the rate is equal to K times the concentration of NO2 squared. Now, let's continue on. C. Consider two possible mechanisms for the decomposition reaction. Is the law described by mechanism 1 shown below consistent with the rate law you wrote in part B? So we wrote in part B, rate is equal to K times the concentration of NO2 squared. Now we have to see if it's consistent. So in this reaction, all we have to worry about is the slow reaction. So the slow reaction, we can combine NO2 and NO2 to form 2NO2, and that means that the rate law for this reaction is going to be essentially the rate of the rate determining step, and that's rate equals K times NO2 squared. So I'd say that for I, this mechanism 1, works because it matches the mechanism we wrote in part B. So that's the answer, and you have to justify it. Well, you could say that the rate of the reaction is essentially the rate of the rate determining step, which is the slow step. And because the rate law of the slow step is K times NO2 squared, then that means that that's the rate law for the entire reaction, and since that matches B, then it's right. So what about mechanism 2? Well, we'll focus on the slow part first. So the rate is equal to the rate determining step, so K times N2O4, and that's all. So I think N2O4 is an intermediate, so we have to try to find a way to substitute that. So we know that the rate of the forward reaction is equal to the rate of the backward reaction since there's a double arrow, and that usually means equilibrium unless otherwise stated. So we know that the rate law of the forward reaction, which is K times NO2 squared, is equal to the backward rate times the concentration of N2O4. So I could label K1 and K negative 1, but in this problem, it seems like they don't want you to label the K, they want you to just write K. So let's just do that at the end. So doing some math, K1 times the concentration of NO2 squared over K negative 1 is equal to the concentration of N2O4. And we can substitute that straight in there, and we get that the rate law for this reaction is equal to, let's see, K times K1 over K negative 1 times the concentration of nitrogen dioxide squared. And remember, since all of these are essentially constants, you can condense them into one constant K. So I could cross that all out and write, well, instead of all this stuff, we can write rate equals K times NO2 squared. And it seems like that matches the original one we found at the beginning. So because of that, mechanism 2 is correct. And we have to justify our answer. So I would say the rate law is determined by the slowest step. So the rate law of the slowest step is K times the concentration of N2O4. But since that's an intermediate, we have to substitute it. So since the forward and backward reactions are equal in equilibrium, we can say that the forward reaction's rate constant times NO2 squared is equal to the backward rate constant times the concentration of N2O4. And doing some math, we get this, and we can substitute all this into here to get that the rate is equal to K, which is the condensed form of all the Ks, times the concentration of NO2 squared. And this is consistent with the rate law we wrote in part B. And if you want the answers that College Board wrote, here it is. So I know that they used this KEQ is equal to this stuff, and that's part of equilibrium, but that's discussed in the next unit. So if you want to, just use my method where you equate the forward and backward reaction and you do the substitution, because both of these methods work, and as you'll see later, rate constants and equilibrium constants are highly related. So you can explain it using words, and you have to be very specific when you're explaining, so make sure to do that and get some good practice in. So that's all for this video. Have a nice day.